In last video, we identified herd immunity threshold, which is 80% in our experiment. Do you think the herd immunity threshold stays the same in every scenario? Or does it shift? How could you test your hypotheses?
Hi, this is Ling from 3D Science Modeling. I'm a science educator and a researcher. I use computer models to help students learn science.
In this video, we're going to use the model to explore if and how the herd immunity threshold change in different situations. Beyond vaccination, our model lets us adjust 3 other factors: population density, transmission rate, and mortality rate. Teachers, a great way to structure this is to divide your class into 3 groups, assigning 1 factor to each group. To test the assigned factor, you will change its value and then rerun the full range of the vaccination tests from 0% to 100%. Then compare the results with your previous 0 to 100% test results. Inside the Google Sheet, you will find the pre-formatted data collection tables under separate tabs for each factor. Go ahead, gather your data, graph, and analyze the patterns. Depending on your available class time, you can set up multiple levels for each factor. It will involve more complicated analysis, but give you more detailed insights into an outbreak. If you're interested, leave your comments below and I will make another video to explain how to do it. Here are some sample data and how to graph them in Google Sheet. Now we have 2 independent variables. If we choose the population density and vaccination rate, and then choose 1 dependent variable, we will not get a graph that clearly shows the pattern. We need to do some organization. Let's insert another column for the dependent variable that we want to plot. For the original dependent variable, let's change the header to population density of 4. For the new column, we're going to change that for population density of 8. Then we're going to cut and paste the data for the density of 8 into the new column. Then we plot the vaccination rate and the 2 levels of dependent variable. It looks the same. Just wait. Now we need to remove the vaccination rate from the series and put it into the x-axis. Then we choose the bar graph, aggregate the vaccination rate, choose the average for the dependent variable. Voila! What did your results reveal? You should notice the following patterns. A denser population requires a higher herd immunity threshold because individuals in a denser population make more frequent contacts. A more contagious pathogen also demands a higher threshold because each affected person spreads the disease more easily. What about mortality? Changing the mortality rate has little to no effect on the herd immunity threshold itself. It only affects the total number of deaths. People may hesitate to get vaccinated for various reasons. Some reasons are medically necessary. Other ideas, however, can be tested right here in our model. First, let's look at natural herd immunity, the idea of letting a disease spread freely so the population naturally develops immunity. While a population can eventually reach immunity this way, our model has shown the devastating cost: a massive spike in infections, severe illness, and unnecessary death. Vaccination allows us to achieve the same herd protection safely without sacrificing lives. Second, let's test the free rider effect, where an unvaccinated individual hopes to rely entirely on everyone else getting vaccinated to stay safe. In our model, We can label individuals to see how likely they are safe when herd immunity has not been achieved. You can right-click in the model to choose an individual person, also called a turtle. Then scroll down to label it. You can make the label color as red so that you can see the label. Make sure you click the return. Then you can watch it, see what happened over time. As we run the model, you can see that being a free rider never guarantees protection. Until the population fully reaches the herd immunity threshold, every unvaccinated individual remains at risk. Now let's see what if the herd immunity has been achieved. Okay, it's a little bit difficult to see, but the individual is still green at the end of the outbreak. He is protected. Let's lock in the 3 big ideas from our model today. Vaccines protect the whole group. As more people get vaccinated, outbreaks shrink fast. Once enough people are protected, we hit herd immunity, which blocks the pathogen from spreading. The threshold changes. There's no single magic number for herd immunity. Crowded places and extra contagious pathogens pull that threshold higher, meaning more people need to be vaccinated to stay safe. Protection takes teamwork. Waiting for natural immunity costs way too many lives, and trying to free ride on other people's protection leaves you wide open to getting sick. If you found this video helpful, please like and subscribe. Share it with more people. Thanks for watching.